Captain Mine, Percy, Illinois, 1967, the second shift. Down in the deepest cut of the active pit, resting directly on top of the black coal seam, sits the Marion 6360. Known universally as the Captain, it is a stripping shovel of incomprehensible scale. It weighs 28 million pounds. While massive walking drag lines operated from the relative safety of the solid ground above the high wall, a stripping shovel lived its entire operational life down in the trench. It sat on the floor, reaching up to carve away the towering wall of overburden, then swinging to cast that dirt into the previously mined cut. The Captain was built to move 180 cubic yards of earth in a single bite. To achieve this, it required a massive, rigid boom and an intricate mechanical crowd system that forced the heavy steel dipper handle forward into the rock face. But before the shovel runner could worry about the high wall, they had to worry about the floor. 28 million pounds exerts terrifying ground-bearing pressure. The machine sat on 8 massive crawler units, each the size of a suburban house. The coal seam beneath these crawlers was the final, valuable product the mine was trying to extract. If the operator misjudged the structural integrity of the pit floor, the machine would not just sink. Its immense weight would pulverize the very coal it was attempting to uncover, instantly destroying the mine's profit margin. Furthermore, beneath the coal lay a bed of soft, unstable fire clay. How did a veteran operator manage to maneuver 14,000 tons of steel across a fragile, high-value floor without crushing the product or sinking into the underlying mud? The Marion 6360 was officially engineered to exert a ground-bearing pressure that theoretically allowed it to float on top of the hard coal seam. The designers achieved this by distributing the 28 million pound mass across the 8 gigantic, motorized crawler tracks, which were mounted to 4 independent steering trucks. On paper, the mathematics of displacement worked perfectly. On the floor of the Captain Mine, the reality was entirely different. The coal seam was not a uniform concrete slab. It contained soft spots, water inclusions, and heavily fractured zones resulting from the blasting above. When a machine of this incomprehensible scale began to sink, it did not happen slowly. If one of the 4 crawler trucks punched through the coal into the soft fire clay below, the massive frame of the shovel would instantly list. Even a 1-degree tilt on a machine towering 20 stories high threw millions of pounds of asymmetrical, twisting stress onto the central pintle bearing and the massive swing rack. The veteran operators could not afford to let the machine settle. They monitored a complex array of mercury leveling switches in the cab, but more importantly, they felt the deck plate. Before we go further, if this kind of content is what you have been looking for, subscribe to the channel. Every video here goes into one machine class at one specific mine, what it was rated for, what it actually ran, and what the experienced operators knew that made the difference between the two. No trade show content. The documented operational reality. Understanding the scale of the Marion 6360 reveals the absolute apex of American mechanical engineering before economics favored smaller, more agile fleets. And leave a comment. If you operated or maintained a stripping shovel in the Illinois basin, what was the specific sound the hydraulic leveling cylinders made when the machine started to lose its footing? In a future video, we will examine the shift to massive hydraulic excavators and why they eventually replaced the rope shovels in selective loading. Now back to the bench. When the mechanical sensors failed to warn the operator of an impending list, how did the physical machinery keep the 28 million pound structure from tipping over entirely? To prevent a catastrophic loss of balance, the Marion 6360 was equipped with a massive, automated hydraulic leveling system. Each of the 4 crawler assemblies was connected to the lower frame by an enormous hydraulic cylinder. As the machine dug, swinging 180 cubic yards of earth off to the side, the center of gravity shifted violently. The hydraulic jacks continuously adjusted, pumping hundreds of gallons of high-pressure fluid to keep the superstructure perfectly level, regardless of what the crawler tracks were resting on. The veteran operator relied on this system, but they never trusted it blindly. They knew that an automated hydraulic system merely masked the deteriorating condition of the floor. As the shovel worked the face, the operator constantly analyzed the physical resistance of the swing. If the swing motors required slightly more amperage to rotate the machine toward the spoil pile, it meant the shovel was fighting an invisible uphill grade. The hydraulic leveling system had compensated for a sinking crawler by extending a cylinder, but the immense mass was still fighting gravity. This was the sensory data that kept the shovel upright. The operator would immediately stop the digging cycle, drop the massive bucket to the ground, and signal the support bulldozers to push fresh, dry material around the sinking track. They had to physically back the machine up to reposition on firmer ground. Steering a 28 million-pound tracked vehicle, however, was an agonizing, mechanical nightmare. The crawlers did not pivot smoothly. What happened to the massive steel track pads when the operator was forced to execute a tight turn to escape a collapsing section of the pit floor? Turning the captain was an exercise in extreme mechanical violence. The machine was technically designed to pivot, with the 4 crawler trucks steering via massive hydraulic cylinders. But turning a 130-foot-long base on solid ground requires overcoming immense friction. When the operator commanded a turn, the outside tracks had to cover more distance than the inside tracks, dragging thousands of tons of steel sideways across the abrasive floor. The operating manual provided specific turning radiuses and procedures, but it could not account for the sheer physical agony of the steel. The heavy pins connecting the individual track pads shrieked and groaned, creating a sound that could be heard miles away across the Illinois prairie. The veteran operator minimized steering at all costs. They planned their cuts hours in advance, ensuring the machine maintained a straight, linear path along the high wall for as long as possible. When a turn was absolutely unavoidable, the operator did not rely simply on the steering controls. They used the massive bucket. They would lower the 180 cubic yard dipper to the ground, embedding the heavy steel teeth into the floor, and use the tremendous power of the crowd and hoist motors to physically push or pull the front of the machine, relieving the lateral stress on the crawler pins. This undocumented maneuver, using the digging implement as a crutch to steer a 28 million-pound machine, required perfect synchronization. If the operator misjudged the application of the hoist brake while pushing against the earth, what was the immediate consequence to the massive structural boom towering above them? If the operator pushed against the pit floor with the massive 180 cubic yard dipper but failed to perfectly modulate the hoist brake, the physical resistance of the earth transferred directly up the dipper handle. Because the dipper was anchored against the unyielding ground, the tremendous force of the crowd motors had nowhere to go but backward. The dipper handle acted as an immense steel lever, physically pushing the 215-foot main boom backward toward the machine housing. This violent mechanical event was known as boom jacking. The operator had only a fraction of a second to sense the upward surge and dump the power. If they reacted too late, the boom would be driven backward until the massive structural suspension cables went slack, and the boom crashed violently into the A-frame gantry, potentially collapsing the entire front end of the 28 million-pound machine. To steer, the veteran operator had to constantly ride this razor-thin edge using just enough downward crowd pressure to lift the front of the tracks, but balancing it with precise hoist tension to keep the boom heavily loaded forward against the suspension cables. It was a terrifying balancing act performed using thousands of tons of steel. To maximize digging force without ripping the machine apart, Marion engineers utilized a highly specific geometry for pushing that dipper into the high wall. How did the unique mechanical linkage of the Marion crowd system physically function when driving a bucket the size of a two-story building into a wall of solid earth? To tear 180 cubic yards of earth from a vertical high wall, the Marion 6360 employed an engineering design known as the knee action crowd. Standard electric shovels used a rack and pinion system mounted directly on the boom to force the dipper handle outward. But at the sheer scale of the captain, mounting the heavy crowd motors halfway up the boom would make the structure impossibly top-heavy and prone to violent twisting. Instead, Marion engineers placed the massive crowd machinery down on the revolving deck, close to the center of gravity. They connected it to the dipper handle via a massive, pivoting gantry framework that resembled a bending human leg. When the operator engaged the crowd, this knee joint extended, driving the heavy steel handle forward. This geometry allowed the machine to transfer the immense digging strain directly down into the rigid main frame, rather than forcing the boom to absorb the bending stress. This mechanical advantage allowed the captain to exert unparalleled breakout force. It could slice through dense shale and heavy clay that would stall a walking dragline. The operator would hoist the massive bucket vertically while simultaneously extending the knee action crowd horizontally, peeling the high wall away in perfect strips. But this mechanical power relied entirely on the assumption that the material would yield. What happened to the regional electrical grid of southern Illinois when that 180 cubic yard bucket struck an unyielding, unblasted seam of solid limestone hidden in the bank? Striking a hard toe of solid rock with maximum crowd and hoist power instantly stalled the massive electric motors housed inside the revolving deck. When the dipper teeth embedded into an immovable seam of limestone, the heavy copper armatures within the motors ground to a violent halt. But the electrical current did not stop flowing. The sudden loss of rotational resistance created an instantaneous massive amp draw that spiked directly backward through the trailing cable. This was not a localized electrical fault. The Marion 6360 operated on a primary power feed that rivaled a small municipality. When the shovel stalled in the bank, the immense surge ripped backward through the mine's dedicated substations and hit the regional Illinois utility grid. The substation breakers were mathematically calibrated to a razor's edge. They had to prevent the shovel from blacking out the surrounding county, yet allow enough transient electrical spike to let the machine physically break the rock. The operator had fractions of a second to sense the stall, feel the hum of the deadlocked motors, and throw the controllers to neutral before the main breakers tripped or the hoist ropes snapped under the immense kinetic shock. The mechanical friction of moving these thousands of tons of steel under such electrical strain required constant, aggressive mitigation. To keep the heavy gears, crawler rollers, and the central pintle bearing from destroying themselves, the machine housed an automated internal lubrication system. What was the fatal flaw hidden within the miles of pressurized grease lines snaking through the dark belly of the 28 million-pound giant? A machine of this incomprehensible scale could not be lubricated manually with hand pumps. To prevent the massive swing gears, hoist drum bearings, and crawler pins from rapidly destroying themselves through friction, the Marion 6360 contained a centralized, automated lubrication system. Heavy hydraulic pumps constantly pushed highly flammable open-gear lubricants and hydraulic fluid through miles of pressurized lines to hundreds of critical pivot points scattered throughout the superstructure. This was the machine's lifeblood, but it was also a fatal liability. Over 26 years of relentless, round-the-clock digging in the Illinois coalfields, thick grease steadily accumulated in the dark, unventilated belly of the lower works. The heavy steel decks beneath the machinery house were coated in a dense, combustible layer of hydrocarbon residue. The interior ambient temperature of the shovel was consistently high due to the immense heat thrown off by the massive electric motors and the friction of the mechanical brakes. The captain had survived the brutal physics of the high wall, the terrifying ground-bearing pressures of the coal seam, and the electrical shocks of the utility grid for nearly 3 decades. It was an immovable fixture of American surface mining. But on September 9, 1991, what catastrophic sequence of mechanical failures turned the heavily lubricated interior deck into an uncontrollable inferno? The destruction of the captain was not caused by a collapse of the high wall or a snapped suspension cable. It was caused by a ruptured hydraulic line in the lower works. As the highly pressurized, atomized hydraulic fluid sprayed into the dark, enclosed space beneath the main deck, it contacted either a heavily friction-heated brake component or an arcing electrical contactor. The ignition was instantaneous. The resulting fire immediately caught the decades of thick, combustible grease caked onto the heavy steel structures of the lower frame. The onboard automated fire suppression systems triggered, but they were vastly outmatched by the sheer volume of fuel feeding the blaze. Within minutes, the fire breached the main machinery house. The immense heat began to melt the heavy copper windings of the hoist and crowd motors, sending thick, toxic black smoke billowing hundreds of feet into the sky above the Illinois prairie. The operators and mechanics evacuated successfully, but the 28-million-pound machine could not be saved. The intensity of the hydrocarbon fire grew so extreme that the heavy steel superstructure of the shovel physically warped and buckled under its own weight. The heat fundamentally destroyed the metallurgical integrity of the gantry and the main housing. The fire burned for hours, completely gutting the mechanical heart of the machine. As the smoke cleared over the Illinois prairie, what dictated the final fate of the 28-million-pound charred remains? The cost to rebuild the electrical systems, the hydraulics, and the structurally compromised main frame of the Marion 6360 was mathematically impossible to justify. The era of the massive stripping shovels had already passed. They were physically constrained to the pit floor, entirely dependent on perfectly blasted rock and brutally expensive to maintain. By the 1990s, the industry had moved toward more versatile walking drag lines and highly mobile hydraulic excavators paired with massive haul trucks. The captain was cut down on site with explosive charges and torches, sold for scrap metal, and erased from the Illinois landscape. What the operating logs showed about how it was managed, how the veteran operators read the strain on the leveling cylinders, how they carefully steered the crawler tracks using the bucket, how they controlled the violent geometry of the knee-action crowd went with the operators when they retired. Some of it was passed down to the next generation of equipment operators. Most of it wasn't. If this video gave you something real, subscribe. More machines, more minds, more of the operational reality that the trade show brochures never contained. Documenting these specific machines is essential to preserving the real industrial history of American surface mining. And if you ran the levers on a stripping shovel in the Illinois basin or turned wrenches in those grease-filled lower works, tell us in the comments. When you were operating a machine of that scale, What was the specific physical vibration that warned you the floor was giving way? In the next video, we will examine the Wabco 120B and the final, desperate stand of mechanical drive-haul trucks against the electric revolution. The most complete operating manual for these machines is in the heads of the people who ran them. Most of it was never written down. The captain is gone. The coal seam is mined out. The machines that pull the earth today are entirely different and know nothing about the massive, brutal physics that once dominated the pit.